Okay, welcome to this webinar where we're going to explain how the digital twin simulations work in the Smart Aquaculture Platform for simulating fishing boats. So we'll go into the code and we'll go into the site. So let me refresh this page and we'll take a closer look. So if you look at this, so I haven't touched this site since Friday when I made the last video about the digital twin simulation, but you can see that the coordinates are rapidly changing on this fishing boat. It's like constantly changing the location. And if you look at the map, then you see this fishing boat just going around in circles around Louisiana. So, so how does this actually work? Um, so at a high level, we are we're doing event-driven programming with an event bus, and you may have also used a message broker, but Java Vert.x um, itself, or Eclipse Vert.x here, this is a reactive application platform that uses the concept of event bus. Let's see. They don't even talk about it on the home page, but it's basically its own message broker. And so the event bus is very powerful because it's its own little message broker that can be clustered and scaled across multiple pods within Kubernetes and OpenShift at the same time. And it's sharing messages. So by default, it'll assign messages coming into this pod and then the next pod and the next pod and the next pod. So every one of these updates happening here every 50 milliseconds is would go to a separate thread or a separate pod every time. So it's built very scalably. And we even use clustered um, clustered Vert.x, although we use Vert.x Zookeeper, and they may actually be, are they moving away from Vert.x or Zookeeper? Um, Clustering API docs. They don't they don't list it here in the clustering section. And I love Zookeeper. I've used it for many years. Um, it's the same thing that powers Apache Solr clustering. So it is possible to choose different cluster managers, but Zookeeper has always worked great for me. And we also use other features like distributed locks and distributed counters to do some really powerful things. Like especially when it comes to metrics, if we're going to track fish population metrics and the number of fish in the ocean for a particular fish population and how fishing boats come in and catch those fish and decrease the fish population, then we would want to use a distributed counter in that instance where multiple fishing boats who run through a fish population decrease the amount of fish in that fish population at the same time that the fish population kind of repopulates through birth, um, fish having babies and increasing the load at the same time. That's a use case for distributed counters. And we use distributed locks within the spine programming tools from Computate, which make sure that if you modify a file and you modify the file again within a couple seconds, that it sets a lock on the file, on the generated files so that they don't get regenerated at the same time and write over each other. You can also use distributed map support where um, you can have a map of key value pairs at the same time. And we have topic-wide subscriber lists and load balancing of all the events coming in on the event bus across pods and threads. So in this way, we can build a very scalable digital twin. Now, if I leave this application alone for too long, it stops updating because I basically get logged out of my session. So I gotta refresh this, and then the data is still flowing. But if you get out of your session, then it'll stop updating the digital twin. So that's going around and around. And the way I wrote this was, we'll just focus on two files right now, FishingBoat.java and FishingBoat ENUS API service impl. So our fishing boat is defined as a map model. The map model gives us the location part of the spine. So this is, let's see, this is a location. It's a geo point, and we say that this is the location of the boat. So we spine program this with some specific fields, some fireware types, geo point, a new row in the user interface for JSON details. If you look at this, there is a, let's see, GeoJSON details. Where's that? Where's the location? Location. Oh, it got overridden to name and description. Okay, so we use doc values in the search engine. We persist it in the database. We give it a display name of location and a description of this GeoJSON reference to the item. I could probably delete this because we really just want it to be a point. But this is the description here that we gave it. And this is what's always updating. But by default, whatever you put in this part of the spine is what it is by default, but it can be overridden, like, and stored in the database instead. But by default, it sets a default map location, which is defined in vars.yaml. So we have some default coordinates where we put something on the map if you don't tell it where it belongs, and which is between Louisiana and Florida a little bit. So we have location, and something that I did last week was there used to be a field in here called area served, but the problem is some models use an area served that's a polygon on the map, and some, like FishingBoat, use a line string. So this is a line string with multiple points in a line. So I had to move it out so that you can specify what it is. So if you look in here, area served, let's see. Yeah, well, okay. I'm having trouble searching, but it's in here. Oh no, I didn't call it area served. I called it path. So this is the path of the fishing boat, and it's of type path, which is a Postgres client data type so that it can be stored in the database. It's also stored in the search engine because Solr can store paths as well, geolocation paths. it's latitude, longitude paths. And we also have a field that's a Boolean field that by default, we set it to be false. So we use this wrap and we do wrap. W.O stands for wrap.object. And then you pass the default value, which is false. But we set this to true when we run the simulation. So when we're here and we toggle the simulation, then it immediately stops when it tries to process the next event. And so this boat is now stopped. Oops. And then if we click this on again, then it'll start simulating again. So we click that on, and then the points start changing. So that's the simulation field, and the simulation delay milliseconds by default is 500, but you see here we configured it to be 50, so we overrode the default value from 500 to 50, and then it gives a much smoother simulation here. Let's see. There's that. And so that's going around. And we add some colors, or we can add colors, titles, and links to our object going around in the map, but still kind of perfecting that. The average speed is how fast this is going around. So if I change the average speed, right now it's set to 100,000. So if I set it to 1,000 instead, and then click out of that, it turns green, and then come down here and you see the boat is going way slower around the ocean. But I can bump it back up again to 100,000, and then the boat starts cruising around much faster. There it goes. So there's some calculations going on with regards to miles per hour and the current location and where the boat is in comparison to this path that's a line string. So we can tweak all these kinds of values, and we can build digital twins for pretty much anything now, because we have a process for that. And when this thing gets spine programmed, it creates it creates 3 API Java classes, or maybe more. It creates this class, FishingBoat ENUS API Surface Impl. And by default, this is empty. So it usually appears like this, but we've added some additional methods and overrode some methods in here to do some specific things. So we override this SQL patch FishingBoat method specifically. And then this extends another class called FishingBoat ENUS Gen API Service Impl. So this is the generated API for fishing boats, which has APIs to search, get, patch, post, delete, import, show the search page, the edit page, the delete filter. And all of these do fine-grained access control before they show anything, because they all require authentication and authorization before you can see the data. So, and some general methods. So this is a class with 3,700 lines of code. And we add to that by extending this SQL patch FishingBoat method to do some GeoJSON. So we actually called the original one here with this super.sql patch fishing boat call. But before we do, we determine, we get the location of the fishing boat, the current location and the current path. And if it's not a refresh request and the path is not null, and the path has at least 2 points in it, and we're not setting the current location. So set location within the JSON object in the request. If it's null, then we let this request go through. And if it's true that we are doing a simulation, then it comes here. But this is not the first part. We'll talk about this part next. What we need to talk about is what comes after you patch the fishing boat, because let's imagine again, I'm going to refresh this and then it's simulating. So I turn off the simulation and it stops. So what happens when I click this on? It's going to come to here. So I can debug this live. So I click this and then it immediately comes to here because we are in the middle of patching this fishing boat request. So we're going to do some checks. We're going to check if set simulation is true. So let me see, let me delete all of these and then put this expression in. Oh, it tells me cannot evaluate. I think let's check if this is true. Okay, so we are in this request, we're setting the simulation to true. If I look at, oh, I'm too late to show you the network request. But what was sent in the body was just one thing, which is set simulation true. So this is true, and this is going to be false because we're not currently simulating. But we check if this is not false. O.get simulation. Let's see, is not false. Oh wait, no, we did. So because this is true, we have an or expression where if this is true, no matter what, we're going to come into this section. And it is true that set simulation in the request is true. So we come in here, we figure out what is the simulation delay millis of this fishing boat. And by default, it's 500, but this one is set to 50. And then we set a timer of 50 milliseconds. So it's not going to enter this method for 50 milliseconds, which is going to be quick, but I'm going to press continue. And then it ends up here. And we do a worker executor.execute blocking, which puts this into the background. If I didn't make this call, then it would only simulate as long as my user session token is valid. And we want to execute this in the background. So we start a background task, which comes in here. And actually, I'm going to come back to this section where everything happens, where we're in the middle of a simulation now. Simulation equals true. And so these are true. That means we're currently simulating things, and we get the time now, and we get the time that the object, the fishing boat, was last modified. So these are two different timestamps, a little bit after each other. And from that, we figure out the duration of this, which is 35 seconds or this many nanoseconds. So in 35 seconds, we're going to calculate how many milliseconds that is, which is this many milliseconds. And then we calculate the average speed in miles per hour, which is, oh, let's see. Let's see what it is for this boat. It says it's, oh yeah, it's 100,000 miles per hour. So it's set very fast. And then what we do is we set two different coordinate reference systems. So if you think about GeoJSON, there's a site, geojson.io, that lets you put points on a map and also line segments like we were doing. So a point on the map looks like this, and it has a longitude and a latitude. I think that's the order that they come in. So these are just 2 points. And it doesn't account for elevation because in this view, the world looks kind of flat and you can identify anywhere in the world with just this and this, but it's ignoring the concept of elevation, how far above sea level you are in the mountains or how far below sea level you are in the ocean. It's ignoring that entirely. It's just a place on the map at whatever elevation it is. So that is WGS 84 coordinates is latitude, longitude. So we call that source CRS. And then we're setting up a different coordinate reference system, Cartesian. And if you look at the wiki page for Cartesian coordinate system, or actually, well, it's basically three-dimensional space. So from the center of the Earth, how far this way or this way or this way, three different coordinates it is. I don't think Cartesian coordinate system, that's not the best page for it, maybe. But on globe, I want to see. Okay, so here's a good picture that shows that from the center of the Earth, the z-axis points through the North Pole, the x-axis goes through the intersection of the equator and the prime meridian, like where Great Britain is, I think. And then the y-axis completes the right-handed system in the equatorial plane. So it's figuring out where you are on the Earth with x, y, and z coordinates. That's why we have to treat these differently and we have to convert between them. So we set up those two coordinate reference systems and we set lenient true to be a little lenient. I don't remember what this SRID is for, but we use it when we set up the geometry factory. And then we calculate the next distance in meters. So based on our duration in milliseconds and our miles per hour, we calculate the next distance in meters. It's going to be that many meters. And set up a tolerance so that we, in case it's not exact, because working with decimal numbers is not exact science, we add some tolerance based on the next distance meters. And we set up a geometry factory. We create a coordinate for the GeoJSON coordinate of our boat at the moment. So that's the latitude, longitude, latitude, X and Y. And then we set up a transform in each of our coordinate systems. And we set we get the old coordinate of the boat and the old point of the boat, then the geometry factory, and then we create coordinates for every point on the line string. So this is gonna loop and give us several coordinates. And in the end, it has 9 coordinates on the line string that are, so what it's done is it's taken GeoJSON and turned it into Cartesian coordinates with 3 axes, X, Y, Z, as well as this old coordinate. Old coordinate is now X, Y, Z, where it used to be latitude, longitude. We've coordinated, we've made it into 3 points instead. All right, so now we keep going. We figure out, is the coordinate on the line? Yes, it's true. Whoa, I'm having like a brownout here. The lights keep flickering. Can you guys still hear me?
Yes, we can hear you. Good, very good.
Okay. Okay, good. We take the line string and we turn it into this index line, which can tell us how far away from our line our boat is. And so the nearest location is basically telling us how far along the line from the given segment index are we? So segment index 3, and we're 0.21% into that segment 3. If we look at this FishingBoat, this is segment 0, this is segment 1, this is segment 2, and this is segment 3. So this is 0.23% or 23% across this segment. Right here is what this is telling us. Or no, what was it? Here's location. It's telling us we're 0.21% across segment 3, 0, 1, 2, 3. And then we get the segment index, which is 3, 0, 1, 2, 3. And we get the next segment index, which is 4. And if the next segment index is greater than the line string dot coordinates dot length, then we set it to 0. So if we get to the end, we need to set the boat to go to 0 again. At least in our current simulation, we want it to go to the dock, but we haven't programmed it that way yet. It just loops. So it's not at the end, so we skip that. And then we get the next coordinate on the line for next segment index, which is 4. And here's the part where we're going to convert this back to GeoJSON, because we found the next coordinate and we're going to find how far we can go within a number of meters in the direction we are planning to go. So we set up this geodetic calculator in Cartesian coordinates, and we get the next geo, which turns this into, it's going to turn it back in the next point into latitude, longitude. So it used to be 0, 0, now it's this, -90, 28. and we set the starting geographic point to be the old location dot getx. We set the destination to be the next geo. So we're telling it that we're here. We want to go to here within latitude longitude coordinates, and we get the direction, which is the azimuth. So that's like maybe radians in a certain direction. And then the next coordinate meters is how many meters it will take to get from here to this next point. And then if the next distance meters compared to next coordinate meters is greater than 0, so the next distance meters we calculated way back here to say, based on our miles per hour and our duration, how far can we go? And it tells us this many meters. So it's probably, it might just be a short jump or it might be a long one because we were actually pausing it um, with this debugging session, but it's not going to be greater than this point. If it's greater than the point, then we just set it to be the next coordinate meters there. So I think it might go in there. Yeah, it's going to go in that section because we were debugging for so long in the beginning. And then the set, and then we set the starting geographic point at old location. And then we set the direction as the azimuth and the next distance meters as a double value. And then we get a new point, and this new point 2D is latitude, longitude. And then we set that location as GeoJSON format. Type point, it looks like this type point coordinates this, that. And then we do a patch request. So that sends the message onto the event bus here. I was talking about the event bus earlier, but it's going to send that event on the message bus with the action of patch fishing boat future. And the body of that request looks like params body. New JSON object. Actually, it's just we already patched it here, and now it at this point. So this goes and patches the fishing boat asynchronously, and then it sets a timer for the next delay in millis, and does a refresh without patching anything at all because it doesn't know what the coordinates are each time. But it just continues, and if I just let this run again, then it's just going to continue on its merry way, updating things, and then we gotta refresh this page, and then we'll see the updates coming in. Yeah, so it's just continuing on. So that is how this event bus driven digital twin works. The next step is to have it integrate with fishing populations to like decrement the count of fish in that fishing population, and then increase the amount of fish within the dock as it returns fish to the dock. Okay, so I've been talking for a long time. Are there any questions?
That is awesome. 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 That is awesome. So Chris, we are in a position now, I think with Jarvis that, we're pretty much we're in position to lead and be as aggressive as we want to. And so we can And then we just have to decide, well, what is the pace and the depth we want to go at expanding spine programming, teaching, and learning. And what I guess one of the things I was trying to do, I was trying to get many little examples because, like for Canada, theirs is due on the 14th if she will respond, and then I got another one going on the 19th. But those could be actual learning examples where maybe we decide what are the five major things we want to teach about spine programming and get those five things into our NSD posters and support interns, so that those five most important things are rooted in us so we're building our community at whatever pace, you decide. So, and we also have the option of maybe doing it with Judith as the rabbit, because
Yeah.
in preparation for, because we don't want to waste time and we want to have it so when it's time, the community is but the wider experience, the more robust your community is. So those are things to think about, and I'll make sure y'all have that, and we can just decide on at what depth we want to go to maybe bring on his community or the Smart Aquaculture community. They could be